Hi, my name is Garth. Like a lot of people, I enjoy theoretical physics. Okay, not, that many people, but it's kind of a hobby of mine. It has been for my whole life, mostly because, it's the world around you. It's what you feel, it's what you know, it's what you see and observe. I mean, if you've played baseball or sports of any kind, and I've played a lot of different sports, physics is a real thing. And theoretical physics is, well, okay, we know how these things operate in our little space. What happens when we look at how these things operate in bigger spaces than us? Literally, how does gravity work across interstellar distances, gamma rays, neutron stars, black holes, all that fun stuff. And there's a really good chance if you're watching this video that you're already somebody who's into that in some way. Uh, I'm doing this video for a very particular reason. However, I have spent the last 25 years looking at some of the things that I don't, consider myself a theoretical physicist because frankly, I don't know the math and I don't have the papers on my wall. As you can see, that's kind of an empty wall. But this isn't empty. At least I hope not. Okay, good. We're there. Here's the thing. Theoretical physicists for a long time have pondered the origins of gravity, dark matter, dark energy, and how things work in the universe. And for a long time, I'm a science geek, uh, a science fiction geek. If you haven't yet, if you consider yourself a science geek and you haven't read any Stephen Baxter, I would say definitely, check him out at your local library or on Amazon or wherever you can get his books. He is an astrophysicist with a great resume who writes fiction, science fiction, and it is crunchy stuff. And it's fun because he explores these things and tries to extrapolate as best as he can. Most theoretical physicists like to extrapolate because, well, I mean, that's the whole point of it, is to say, okay, well, we stand here, what are we looking at over there? Well, for over 25 years, I have had a model that I have done for people to try and help them understand how gravity works. And when I first explained this model, when I first introduced this model to a friend of mine, Bernie, hi, hope you're doing okay, buddy. Bern, he said, well, that's an interesting mental exercise. And then a few years later, he came to me and said, hey, do you remember that model that you explained to me? And I said, well, of course. He said, well, I didn't know it at the time, but it actually illustrates the anti-gravitational aspect of the cosmological constant that scientists just now, and this was like 1998 or 2000, it was late 90s, and I don't remember exactly when, that theoretical physicists had figured out that there was an anti-gravitational aspect to the cosmological constant, because of course we're looking at lambda being the cosmological constant, the expansion of the universe. And he said, yeah, that was in your model. And I said, oh, well, yes, I know. So over the years, I've shared this model with people, and for many of them, for sadly most of them, it goes completely over their heads. For the people that invest themselves in it, picture it, try to understand it, it's a bit enlightening, because in this model is contained Einstein's lambda, the expansion of the universe, the anti-gravitational aspect of the cosmological constant, as well as an explanation for dark matter slash energy. Same thing. Dark matter, dark energy, whatever. It's the same thing. And for 2 decades, I've just, punted this thing around. I tried actually reaching out to theoretical physicists, gravitational theorists, and said, hey, you know what? I think we might be looking at this all wrong. And of course, they have papers on their wall, lots of papers. And one of the things that I've noticed about people with a lot of papers on their wall is that their noses sometimes tend to knock satellites out of orbit. Because, nobody ever got back to me. That's okay. I mean, I'm a nobody. I don't actually have a degree in this. I've pursued a number of things. I've studied a number of things. I've spent thousands of hours on this, and my only weakness is math. I picked up a book on it, and I tried to learn the math that dealt with quantum theory, and I kind of got it, but it wasn't something that I could actually go up on a stage and say, look at this, and prove anything, because that's, that takes a long time, and even the people who are well versed in it have trouble doing that. So, but what I'm about to do is I'm about to share with you a model, and all you have to do is picture it. You don't have to know any math. You don't really have to think too hard, but you should think some. But if you can imagine, if you can picture things, then after this video, after you're done watching this, you may never see gravity the same way as you have your whole life, because it doesn't work the way that most people, or at least the theoretical physicists, think. Let's just say that after I do this, you get it. You will understand lambda, Einstein's, theory of cosmological expansion, the cosmological constant, which became, of course, the Hubble constant, because he refined the math and said, oh, wait, no, it's exactly like this. And he proved Einstein right. But there's more to it than that. One of the things that theoretical physicists cannot tell you is how gravity is generated. They can't. They can tell you what gravity is. They can tell you in reams of volumes and with the waterfalls of math how it works. But they can't tell you where it comes from, what actually causes it. And that, to me, is such a telling thing, because I have known this since I was like 3 years old, 5, 6-ish. I've known, and a lot of us have, because we can all feel it. Now, this isn't some flat earth bullshit, trust me. Flat earthers are the other end of the spectrum, dumb fucks that I deal with, just like because I like kicking sand in the face of kindergartners on a playground. And by that I mean full-grown adults who think they know what they're talking about, but act like kindergartners. So yeah, I like kicking sand in their faces. And of course the sand is actual math, and not that I'm that good at math, but no, this is something which, when we're done, you will see in a different way. And this theory will reconcile with gravitational theory across the board. But let's start with the model, just because. Now, it helps to stand up and close your eyes. You don't have to do this. You can sit in your chair. You can hold your arm out. I do recommend that. But whatever it takes to help you picture this will actually be very useful to getting that image to you, so that you understand it and can feel it, so that you'll never see gravity the same way again. So let's start. First, clear your head of all the stupid stuff. Leave my voice if you can. A lot of people have trouble with that, but whatever. Clear your head. Picture yourself in a room. The room is empty. The walls are white, as is the floor and the ceiling. It's okay. You're not trapped. You'll get out soon enough. But for now, you're in the room, and you're standing in the room. This is when you should be standing, if it helps. So standing in the room, in your outstretched arm, you hold a red ball. All right, it's a pear, but close enough. But you're holding a ball in your hand in the room. Now, you, the room, and the ball in your hand are all growing at exactly the same rate. What do you notice? Now, I've done this probably 1,000 times, or at least with 1,000 people. It's been 20 some odd years, and I love doing this one. It's great at parties, and sometimes people get it. Sometimes people get it right away. Not usually, though, because there's 2 more steps to this. But if you're in the room, standing up and holding a ball in your hand, and you, the room that you're in, and the ball in your hand are all growing at an ever accelerating rate. Give something away. Are all growing. What do you notice? Now, most people will say, wow, if the room and I am growing at the same rate, and the ball in my hand is growing at the same rate, if everything is growing at the same rate, I notice nothing. Now, these are the clever people. I've heard all the things that dumb people say. And they're like, well, if I'm just going to get bigger, I'll fill the room. And I'm like, no, you just, no, because the room is growing and the ball is, so I'll get bigger than the ball. No, that's not how that works. And, okay, fine. And then the super clever people are like, well, what about the air? And if I'm getting bigger and the air is more dense, no, because it's happening with the air too, but that's another story. Okay, so we have all of that, but that's irrelevant. All right, this is happening at the level of quantum foam. Okay, so you are standing in a room holding a ball in your hand, and you, the room, and the ball are all growing at an ever accelerating rate. The really, really clever people, and some of you have already caught up, some of you have already figured it out, will say, well, if the ball is getting bigger and my hand is getting bigger, then I'm going to feel some pressure between my hand and the ball. Okay, now I've seen that about 1% of people figure that part out, and it's usually because they separate the idea of, well, where the room is from anything else. I can't get into that yet. Not until we get to the second part. The second part. Picture yourself once again standing in a room holding a ball in your outstretched hand. You are in this room with the ball in your hand, but the room that you are standing in is setting right on the surface of a gigantic ball. And we'll make that ball red. A ginormous red ball. The room that you're standing in is sitting on the surface of a ginormous red ball, a red ball so huge you can barely fathom it, but it's huge. Now, you, the ball in your hand, the room that you're standing in, and the ginormous red ball beneath your feet are all growing at exactly the same rate. The same ever accelerating rate. Now what do you notice? Take your time. So you're in the room. You're holding a ball. The room is getting bigger. You're getting bigger. The ball is getting bigger. The ball beneath your feet is getting bigger. What do you notice? Well, if everything's getting bigger, you don't notice anything, right? Wrong. Because if the ball beneath your feet is getting bigger and bigger at an ever accelerating rate, then remember that feeling of holding that ever expanding ball in your hand and feeling like that ball in your hand was pushing against your hand as your hand pushed against the ball? Well, if there's a ginormous ball below your feet that is growing at an ever accelerating rate that doesn't stop, then what do you notice? Okay, if it hasn't come to you yet, all I want you all to do is look down and realize that ball is right beneath your feet right now. Gravity is not a pulling force. Gravity does not pull you towards the planet's surface. Literally everything in the universe is expanding in accordance with the cosmological constant, the Hubble constant, at an ever accelerating rate. That means that we have such a simple formula that theoretical physicists already use. Time times mass equals gravity. If you have a massive object, the more massive it is, even if it's tiny, even if it's, what do I got? Let's see, it's a bread clip. Okay, if we have a neutronium bread clip and it is made of neutronium and accelerating at the cosmological constant, it would like literally crush everything in this room instantly, including me and this computer and everything. So, whatever. But the more massive something is, the more of an effect the cosmological constant has on it. That is gravity. It is that simple. Gravity is not a pulling force. It never has been. Duh. Okay? What gravity is the literal crush of the universe expanding in all directions and in every way, and the space. Like you're in the room, remember. Being in the room, remember. Because the room is expanding, so is the space between you and the walls of the room. That space is expanding too. That's the cosmological constant. Look at what they say about galaxies. Okay, galaxies that are furthest apart seem to be moving away from each other at the highest rates of acceleration. Well, yeah, it's because they have more space between them. Well, what does that mean? It means time times mass equals gravity. Time times space equals acceleration. You could even say mass. Time times space equals space, and more space on top of that. Well, it acts like mass, doesn't it? Pushes things apart. Okay, well, I'm not gonna speculate on how that could explain dark energy or matter, dark energy slash matter, or dark matter slash energy, whatever. It's all the same. But what we are looking at is the fact that we have looked at gravity all wrong for a very long time. It's so simple, and yes, we would have to reconcile that with everything. Well, okay, when we actually look at inverting the formula, everything reconciles with it. Black holes still operate the same way, except that, instead of these greedy bastards that keep shrinking, we realize they're greedy bastards that are actually expanding, gobbling up the space around them, like voraciously in all directions. And oh, thank God there's enough space between them and us that keeps that space, okay, pushing against them, that keeps that space, what's the opposite of contracting? Expanding. Thank you very much. It keeps that space expanding around those black holes, that keeps them isolated because they are reaching out. They're growing, accelerating. Yes, it reconciles with black holes. Here's another thing that it reconciles with. And this is one for the true theoretical physicists. It actually reconciles with remote object gravimetric lensing. Oh yes, you take that distant, like, star, that distant neutron star. We'll take a neutron star. Neutron stars, they're heavy. Okay, we'll take like a neutron star or something, and we'll watch light bend around that. Well, you know what? It's not the gravity of that neutron star pulling that light around it. Okay, it is the relative forces of the space around that neutron star as that neutron star expands that are making that bend seem to happen. That's what's really happening. So maybe you followed all of this. Great. Maybe you didn't. That's fine. Watch it again. Can't hurt. Run the model. The model where you're in the room with the ball and doing the thing, and the room is getting bigger, and the ball is getting bigger, and you're getting bigger, and the thing below you is getting bigger. The ball below you is getting bigger at an ever accelerating rate, because that's what the cosmological constant is. I mean, it, 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 it's reproductive of the speed of light, basically. Okay, the speed of light is a fascinating thing. It's like it's the speed limit that the cosmological constant can operate in, and the speed of light is actually an acceleration. But maybe I'm stupid. I don't know. But we're looking at gravity wrong, and when we figure that part out, we'll look at empty space, and how empty space is doing all this pushing and has all this turbulence to it. And we'll say, oh, wow, well, now we understand dark matter / energy. And one thing that I think I have to leave off on is that if my theory is correct, here's what we're going to see. If constant, how would I put this? Cosmologically constant generated inverse gravitational theory is correct. I sure hope somebody can come up with a better name for it than that. But still, okay, if that is correct, and I believe that it is, then here's what we can expect to see. We can expect to see hypermassive objects, okay, at great distances from each other. And if we look at the space between those hypermassive objects, we will see distortions. We'll see distortions somewhere in that middle space between these hyper massive objects. So let's take galaxies that are flying away from each other at like breakneck speed, but they're hypermassive. Okay. What we'll see between them is gravitational wave compressions. Now, it's going to depend on which is more massive than the other. If one is twice as massive, we can expect to see the compression shifted a little towards the one that's lighter. But we can look around for this. We can see this. All right. If we see a black hole and a black hole, and they're moving away from each other, now we can look between them and say, hey, what kind of spatial distortions are going on here? And we will see time-space distortions between these hypermassive objects that are moving away from each other. Now, what would be really interesting is to see hypermassive objects moving towards each other. We'll have to look into that, though, because, I haven't seen anything about that. Most everything in the universe is moving away from everything else because, of the cosmological constant. And because the universe is expanding in not just space, but time, space-time, if you will, everything seems to be moving apart from everything else. And the space in between things is part of that expansion because the cosmological constant, okay, at some level, works not just on mass and matter, but on space. And the space between things gets bigger too. And somewhere in there, we'll figure out dark matter. In the meanwhile, maybe I'm crazy. Maybe I don't know anything. I don't have pieces of paper on my wall. No. I might have, but that's another story, another iteration of the multiverse. But here and now, all I can say is I have a model, and the model makes it apparent that we should at least take another look at how we've been looking at things. Give it a try.